those wascally wabbits are we producing? Rapidly. How can we model such change? With calculus, because calculus is the science of continuous change. As we saw in lesson 1.1, functions are used to model change. In lesson 1.1, we use the simplest kinds of functions to model change. They're called linear functions. In general, linear functions are typically written in what's called slope-intercept form. Y equals f of x equals mx plus b. X is the independent variable, the input for the function f. You evaluate this function at the number x by multiplying m times x and then adding b. M and b are constants. The resulting number that you get is called y. That's the dependent variable or output. The constant m represents what's called the slope of the linear function. It's also the rate of change of y with respect to x. For every 1 unit that x increases, y changes by m units. That change will be positive if m is positive and negative if m is negative. In other words, the graph of f is increasing as x moves to the right when the slope m is positive, and it's decreasing as x moves to the right when the slope m is negative. In this picture, look at the blue legs of the right triangle. The rise of this function is negative 2.3 because the function is decreasing, while the run across the top is 4. The ratio negative 2.3 divided by 4, which is about negative 0.57, is the slope or rate of change of y with respect to x. For every 1 unit that x increases, y decreases by about 0.57 units. Again, the slope is rise over run, which can be found in this way. If x1, y1 and x2, y2 are 2 distinct points on the line, then rise over run is y2 minus y1 divided by x2 minus x1, commonly written with capital delta notation, delta y over delta x. Capital delta is shorthand for change in. The letter b represents what's called the y-intercept of the function. It is the initial value of the function when x equals 0. In other words, it's f of 0. And if you've got a point x1, y1 on the line, it can be found by doing y1 minus m times x1. Linear growth occurs at a steady rate. Here, the number of dots increases by exactly 100 for each time step. On the other hand, exponential growth, while it can start out slow, can eventually grow incredibly fast. Here, the number of dots doubles for each time step. Here's a graphical comparison. The linear growth in blue is a straight line, while the exponential growth in red is concave up and eventually grows very rapidly. Exponential growth always beats out linear growth in the long run. We say exponential growth dominates linear growth. Let's look at this exponential growth example more carefully to see if we can see a pattern that will give us a formula. This is an example of doubling growth. If y increases by a factor of 2, it doubles. For every 1 unit increase of time t, this is what's called a relative growth rate or percent growth rate of 100% per unit increase of t. Doubling is 100% growth. We want our function to be of the form y equals f of t. Here's a table of values. If we assume our function starts out with a value of 1 when t equals 0, then it has to double to 2 when t equals 1, then double again to 4 when t equals 2, double again to 8 when t equals 3, etc. Instead of adding a constant amount each time the independent variable increases by 1 unit, as we did with linear functions, we are multiplying by a constant amount. Since 1 equals 2 to the 0 power, 2 equals 2 to the first power, 4 equals 2 to the second power, 8 equals 2 to the third power, 16 equals 2 to the fourth power, etc., the pattern indicates that the function is y equals f of t equals 2 to the t power. What if the initial value of y is something other than 1, and y triples instead of doubles for every 1 unit increase of t? If y increases by a factor of 3, it triples. For every 1 unit increase of time t, this corresponds to a relative or percent growth rate of 200% per unit increase of t. If our function again is y equals f of t, here's a table of values if I also assume that y equals 2 when t equals 0, and then when t is 1, y triples to 6. When t equals 2, y triples again to 18. When t equals 3, y triples again to 54, etc. Since 2 equals 2 times 3 to the 0 power, 6 equals 2 times 3 to the first power, 18 equals 2 times 3 to the second power, 54 equals 2 times 3 to the third power, etc. The pattern indicates that the function is y equals f of t equals 2 times 3 to the t power. When you see this formula, you need to think about order of operations. 3 to the t power gets done first, then you multiply by 2. As you can see graphically, tripling growth in red is much faster than doubling growth in blue, and that would be true even if the initial value for the tripling was smaller than the initial value for the doubling. If you're comparing two exponential functions, the one with the bigger base dominates in the long run. The base is 2 for the doubling function in blue and 3 for the tripling function in red. Let's now look at a common application of exponential growth functions, savings accounts. Suppose Bobby deposits $500 into a savings account earning 4% annual interest compounded quarterly, and Cindy deposits $400 into a savings account earning 6% annual interest compounded monthly. The word nominal is in both spots because of the compounding. The fact that compound interest is earned means that they actually earn more than the percentages that are given, so those percentages are in name only. We're interested in answering two questions. First, what relative growth rate do they each earn per year? And secondly, when does Cindy's account balance grow bigger than Bobby's? After all, Cindy has a higher interest rate and her account is being compounded more often. We will not get into the details of compound interest other than to say that you are earning interest on not only your original balance, but also interest you've already earned. Here is its formula. A equals P times the quantity, 1 plus R over N to the N times T power. In this formula, A represents the account balance. It's ultimately going to be a function of time t in years. P is called the principal. It's the initial deposit. R is the nominal annual interest rate compounded N times per year. You see N in the formula in two spots. Remember that Bobby deposited $500 at 4% compounded quarterly. N equals 4. This ultimately means that Bobby earns about 4.06% per year. Here's how to see why. Bobby's amount A is a function B of t, where t is time in years, P is 500, R is 0.04, N is 4, it occurs again twice. 1 plus 0.04 over 4 simplifies to 1.01, and by properties of exponents, the 4 times t here can be separated out into a 4th power here and a tth power there. When you use your calculator to find 1.01 to the 4th power, you get about 1.0406. That's the base of this exponential function, and that means Bobby earns about 4.06% growth per year. On the other hand, Cindy earns about 6.17% per year. Her amount, A, is a function C of time t. Based on her $400 initial deposit, her 6% annual interest rate compounded 12 times per year. 1 plus 0.06 over 12 simplifies to 1.005. Once again, 12 times t can be separated into a power 12 here and a power t there. When you compute 1.005 to the 12th power, you get about 1.0617, which means Cindy's percent rate of growth is about 6.17% per year. We don't yet have the algebraic tools to figure out when Cindy's amount passes Bobby's, so let's take a graphical approach. The red graph shows Bobby's amount with interest accruing every quarter, while the blue graph shows Cindy's amount with interest accruing every month. You can see that eventually Cindy's graph does catch up and pass Bobby's graph. Using technology, their point of intersection can be found to have coordinates t, A is approximately 11.1, 779. In other words, Cindy passes Bobby after about 11.1 years when both of their balances are about $779. Now, you might wonder, and it's even important to wonder for calculus, are these graphs that were drawn truly continuous with no breaks in them? After all, what does it even mean to raise a number to a fractional or even irrational power? Have you ever thought about that before? It's not an easy question to answer. Secondly, should they be continuous for the application? After all, interest is not earned continuously, is it? Don't banks just give you interest at certain moments in time? And third, what happens if the number n of compounding periods per year gets very large? Does the amount of growth skyrocket? We will address these questions, but for the moment, let's work on generalizing what we've learned about exponential functions, including to the case of exponential decay. The form we will use for exponential functions is this. P will be our dependent variable and t will be our independent variable. We will write P equals f of t equals P sub 0, which represents one number, times a to the t power. Realize you need to do a to the t power first before multiplying by p sub 0. Alternatively, equals p sub 0 times the quantity 1 plus r to the t power, where evidently a equals 1 plus r here. For almost all applications, we want p0 to be positive, a to be positive, and a to not equal 1 because that gives a constant function. A represents the base of this exponential function. It can also be described as the change factor per unit of time. It's a growth factor when it's bigger than 1, and it's a decay factor when it's less than 1. If we multiply it by a to the t over a to the t, which doesn't change its value because that's just multiplying by 1, we can then use a property of exponents to write the numerator as a to the t plus 1 and represent a ultimately as f of t plus 1 divided by f of t. This works no matter what t is, and it also implies that f of t plus 1 is a times f of t, justifying the name change factor per unit time. The letter R represents the relative or percent change rate per unit time. Since a equals 1 plus r, that means r equals a minus 1. Think about our examples. For the doubling case, when a is 2, r is 1 or 100%. For the tripling case, when a is 3, r is 2 or 200%. If, for example, a is 1.1, that corresponds to r equaling 0.1 or 10% relative rate of growth. By replacing a with f of t plus 1 divided by f of t and getting a common denominator of f of t, we can also write it as this fraction. It's the amount of growth in the time interval, f of t plus 1 minus f of t, divided by the starting amount, f of t. What do graphs in these two cases typically look like? For the growth case, when a is bigger than 1 and r is bigger than 0, the graph looks like this. It's defined for all real numbers t, it's always increasing, it rises as t moves to the right, and it's also concave up. What concave up really means is that the slope of this curve keeps increasing. On the other hand, in the decay case, a is between 0 and 1, and r is between -1 and 0. r is negative. The graph looks like this. It once again is defined for all real values of t, but this time it's decreasing. However, in spite of the fact that it's decreasing, it's still concave up. The slope of this curve, in spite of being negative, keeps getting bigger because it keeps getting closer and closer to 0 as t moves to the right. Let's do a quick example of exponential decay. Depreciation of assets, such as cars, is an important fact in life. Suppose you buy a new car for $30,000. Also suppose it depreciates, decreases in value, at a constant relative rate of 18% per year. Our first goal is to represent the value V of the car in dollars as a function of time t in years. Our second goal is to find out how long it will take until the value of the car is $5,000. Because the car depreciates at a constant relative rate, an exponential function is appropriate. We can write the value v as a function f of t that equals v sub 0, the initial value of the car, times a to the t. The depreciation relative rate is 18% per year. That means we could say the change relative rate is negative 18% per year. In other words, r is negative 0.18. We can replace v0 with 30,000 and a with 1 minus 0.18. When you simplify that, that becomes 30,000 times 0.82 to the t power. For every year that passes, the value of the car is 82% of the previous year's value. As in the previous application, we don't have the algebraic tools to solve for when the value gets to $5,000. So we again take a graphical approach, and we see that it takes a little over 9 years. Let's go back to compound interest now and address the question of what happens as the number of compounding periods gets larger and larger. Here again is the compound interest formula. A equals p times 1 plus r over n to the n times t power. Again, what happens as n gets bigger and bigger? Let's keep things simple and assume that p equals 1, r equals 1, and t equals 1. We're going to keep track of the value of a equals f of 1 to fractions of a cent so we can see distinctions. Here's a table of values when n increases to higher and higher powers of 10. When n is 1, p has doubled from 1 to 2 because you had 100% growth compounded once. When n is 10, it turns out that p has grown from 1 to 2.59374. Interest was compounded 10 times in the year at a rate of 1 divided by 10.1 or 10% each time. When n equals 100, so that you get 1% interest 100 times in 1 year, then $1 grows to $2.70481. As n keeps increasing to 1,000, then 10,000, then 100,000, then 1,000,000, we continue to see a increase, but then it gets to a point where it doesn't seem to increase anymore. We reach this point where it becomes 2.71828, and if you do continue trying to make n even bigger and bigger, you will never get past this amount. This amount is an approximation to the so-called limiting value of a as n goes to infinity. What is this limiting value? It's called the number e and we write e as the limit, lim, as n goes to infinity of the expression 1 plus 1 over n all to the n power. Here are its first 25 digits. E is 2.718281828, as if it's going to repeat, but then it doesn't repeat. 459045235360287, blah, blah, blah. This is a very special, irrational number, just like pi is. It's not rational. It's not a repeating decimal. All this might seem a bit vague. What does it really mean to approach this number? And what does it mean for n to go to infinity? After all, infinity is not a number, is it? In fact, the limit concept and how we treat infinity is at the heart of what distinguishes calculus from plain old algebra and pre-calculus. We could also ask what happens in the general case for compound interest as n approaches infinity. We can write the general formula with an extra limit sign in front, letting n go to infinity. Without justification, we can bring this limit sign inside the parentheses here after we've used the rule for exponents, where we can separate the n and the t powers like this and this, and then it turns out that that limit equals e to the r power, where r is the continuous annual interest rate. Simplifying, we get this formula that a equals p times e to the r times t power. Can interest truly be compounded continuously? Essentially, this formula allows us to define how it can. We can also go back to our application and ask what effective annual rate does Bobby earn if his 4% nominal interest rate is compounded continuously instead of quarterly. Here are the details for how to figure it out. Use the formula that we just derived, a equals p times e to the rt power, replace p with 500 and r with 0.04, then use a property of exponents again. The 0.04 and the t can be separated out as shown. Now use your calculator to approximate e to the 0.04 power. You should get about 1.040811. This means Bobby earns about 4.0811% per year. That's his effective annual interest rate. In general, what's the relationship between exponential functions as we've written them so far and exponential functions with base e? Remember that the form so far is like this. P equals f of t equals p sub 0 times a to the t, where a is the change factor per unit time, which can also be written as p0 times 1 plus r to the t, where r is the relative change rate per unit time. And yes, a does equal 1 plus r, so r equals a minus 1. We can also now write this as p sub 0 times e to the kt, where k is the continuous relative rate of change per unit time. In the case of compound interest, it's the continuous compounding rate, which we called r on the previous slide. And the relationship between these things can be expressed this way. E to the k equals a, where e is about 2.71828182846. And remember, a does equal f of t plus 1 over f of t. E to the k is the change factor per unit time. For exponential growth, a is bigger than 1 and k is positive. And for exponential decay, a is between 0 and 1 and k is negative. For most practical situations, k is slightly less than r, which means it's slightly less than a minus 1. To find k, we need the natural logarithm. More about that in a later lesson. It should also be remarked that in the case of exponential decay, we sometimes replace k with negative k, and we say that e to the negative k equals a, and call k a continuous relative rate of decay per unit time. In that case, k would be positive, so that negative k is negative. Before we end this video with a brief discussion about continuity, we should also briefly discuss the concept of doubling time and half-life. No matter what the starting amount is, the value of a and r and k determine the doubling time in the case of exponential growth, or the half-life in the case of exponential decay. For exponential growth, we are after a time t where 2 times p0 equals p0 times a to the t. In other words, p0 has doubled to 2 times p0. The p0 on both sides can cancel. The starting amount doesn't matter, making the equation become a to the t equals 2. It turns out this equation has a unique positive solution that we label t equals log base a of 2. Don't worry about what this symbol means yet. In the case of exponential decay, we set 1/2 p0 equal to p0 times a to the t. We cancel the p0s again and get a to the t equals 1/2, and we can say this has a unique positive solution that we label t equals log base a of 1/2. At the moment, we can only solve for these things graphically. For the case p equals 1.1 to the t, we see that p doubles from 1 to 2 when t is approximately 7.27. That's the doubling time. Let's end lesson 1.2 with a very brief discussion of continuity. More about continuity will come in a later lesson. Exponential functions are continuous. Their graphs have no breaks in them. Rigorously proving this fact is very difficult. We're not going to do so. Part of the difficulty stems from something even more basic, defining what it means to raise a positive real number to a rational power and, especially, an irrational power. You define what it means to raise a positive real number to a rational power like this. For a positive real number a and integers m and n, where n is not 0, a to the m over n power can be defined in one of two ways, either as the nth root of a to the m power or the mth power of the nth root of a. For example, 8 to the 2/3 power can be thought of as the cube root of 8 squared, which is the cube root of 64, which is 4, but 4 is also 2 squared, which is the same as the cube root of 8, quantity squared. What about irrational powers? It turns out that limits come to the rescue. The reason being that irrational numbers are limits of rational numbers. Finally, if you want to be extra technical about it, in the application to compound interest, the actual balance is actually a discontinuous function. We were only using the exponential function to approximate it. Thanks for watching lesson 1.2 of Calculus 1.